Hello, everyone. Today we're going to talk about another way to write numbers in different ways and see how they compare to each other. And today we're going to talk specifically about scientific notation. We're going to write numbers in standard form or regular form, some would call it. And we're going to take those numbers and we're going to rewrite them in scientific notation or vice versa. We're going to transfer numbers between standard form and scientific notation back and forth. So what is scientific notation? That's our vocabulary today. Scientific notation is a way to take very large numbers, very large, I'm talking millions, billions, trillions, large numbers with lots of zeros at the end, or very, very, very small numbers, like microscopic measurements, like 0.0000000 something. And I'm talking that small. So scientific notation is a number, it's going to be a decimal number, and it's going to have a power of 10 factor. So here's the form. A is going to represent a number, a decimal number. A number is between 1 and 10. So there's going to be some sort of number here like 2.3 or 5.9 or 2.61 or just 7 times 10 to some power. And that some power is going to tell us how many times to move a decimal point in that number to convert it back and forth. Here's an example. 425 million, a very large number, can be written in the form 4.25 times 10 to the 8th power. 4.25 is my decimal between 1 and 10. Notice there's only a single digit, one digit before the decimal point. That's really important. It can only be one digit before the decimal point. In this case, it's a 4. Times 10 to the 8th power. The 8th power tells me I moved the decimal point 8 places to get from where it is in the beginning at the end of the number to where it is at the end between the 4 and the 2. Let's see how it works. Oh, so numbers that are very large have a positive exponent. This is a key concept, basic concept to remember for all of these. Very large numbers have a positive exponent on the 10. That's because you have to repeatedly multiply, do repeated multiplication by 10 to make that large number. So you take that decimal, keep multiplying by a bunch of 10s to make the number very large. That's why you have a positive exponent on the 10. And numbers that are very small have a negative exponent on the 10. Because if you have a decimal number, you want to make it very, very, very small, you have to keep on dividing by 10. And dividing by 10 is a negative exponent. Remember, 10 to a negative 1 power means to divide by 10. 10 to the negative 5 power means to divide by 10 5 times, divide by 5 tens. So you have to do repeated division. That's why I'll have a negative exponent. Very important concept. Positive exponent, large numbers. Negative exponent, teeny tiny microscopic decimals. Let's take a look at some. 5.34 times 10 to the 4th power is written in scientific notation. They wanted to write this in standard form. Well, 10 to the 4th power is a positive exponent, so I know my number is going to be large. It's not going to be small. Therefore, I'm going to be multiplying by 10 a bunch of times, 4 times specifically this time. So that means multiplying by 10 4 times is going to move the decimal point 4 places. It's going to move it over 1 place, 2 places, and now I'm out of space. So I need to move it 2 more spaces, 3 and 4. And these 2 blanks right here are going to get filled in by zeros to fill out my final number. So move it over 1, 2, and then 3, 4 filled in with zeros, and my answer is 53,400. So I moved the decimal place 4 places, the decimal point 4 places. Same thing here. Let me just delete that. 9.62 times 10 to the 5th power. Well, I have my 9.62, and my exponent is positive. Therefore, I'm going to make a large number. Therefore, I'm going to move the decimal to the right to make that number large. I'm going to move that decimal 5 places. So I go 1 place, 2 places, and then I have 1, 2, 3 more to make 5 places. And those last 3 places have to get filled in with placeholder zeros. So therefore, my final answer is 962,000. See how I filled in with the zeros? Okay. The opposite of that is when I have a negative exponent. 3.27 times 10 to the negative 3rd power. Exponent's negative. Therefore, it's going to make a very small number, a teeny tiny decimal. And I'm going to move the decimal point, in this case, 3 places. And to make it small, I'm going to move it to the left. So if I move it to the left, I go 1 place. And now I have 2 and 3. There's my new decimal point right there in the front. I need to fill in these 2 empty loops with some zeros. And my final answer is 0.00327. You don't have to put the 0 in front. I generally don't. I just make my decimal nice and bold. The only reason why there's a 0 there is to identify the fact that there's a decimal point right there. You don't have to put a 0. You can just put 0.00327. Okay? Let's do another one like that. 2.85 times 10 to the negative 5th. I'm going to move that decimal place 5 places to the left because a negative exponent means it's going to become a very small decimal. So 2.85 is my original number. I'm going to move that decimal point 5 places to the left. 1, and then 2, 3, 4, 5. There's my new decimal point. And these 4 places are going to get filled in with placeholder zeros. Let's take a look. 0.0000285. That's how I convert from standard form, or from scientific notation into standard form. Now I'll do the opposite. I'm now going to convert from standard form, a regular number, into scientific notation. Remember, in a regular number like this, the decimal point always starts out at the end of the number. And scientific notation said there can only be 1 digit before the decimal place, only 1. So this decimal point has to move over, so there's only 1 number in front of it. It's going to move over to here, between the 3 and the 7. It's going to have to move from here to here. Well, the question is going to be, how many places is that? So you're going to count your places. And how many places it moves is what your exponent's going to be. In this case, it moves 6 places. 1, 2, 3 by zeros, 4, 5, 6, puts it in the new place, 3.725. And because you notice it's a very large number, you know that my exponent on a large number is always a positive exponent. So it moves 6 places, so my exponent is going to be 10 to the 6th power. 3.725 times 10 to the 6th power. Notice we keep all the numbers that are not zeros and drop off all the zeros at the end. It's supposed to shorten the number. In this case, it doesn't shorten it a whole lot because there are quite a few of these non-zero numbers and not a lot of zeros. If we were talking trillions or quadrillions or quintillions, now we're talking massive number, lots of zeros we have to get rid of. This really does shorten the number. 931,500,000. Right now the decimal point is at the end. I need to move it over so there's only 1 digit in front of it. It's going to move all the way over between the 9 and the 3 here. It's going to move this whole distance. So how many places did it move? Well, let's see. 1, 2, 3 to the comma. 4, 5, 6 to the next comma. 7, 8. It moved 8 places. It's a very large number, so that means my exponent is going to be positive. It's going to be 10 to the 8th power. 9.315 times 10 to the 8th power. Now we'll do it the other way. Tiny, teeny decimal, microscopic. I need to move my decimal point over so there's only 1 digit in front of it. It has to move right here between the 3 and the 1, so it'll be 3.16. So I need to move it from where it is this way. How many places did it go? 1, 2, 3. It looks like it went 4 places. Decimal point moves 4 places. Therefore, my exponent is going to be 4, but it's a tiny microscopic number, so it's not really going to be 4. It's really going to be -4 because I have to keep on dividing by 10 to get that tiny decimal. So it's 3.16 times 10 to the -4th power. One more like that. Move my decimal over so there's only 1 digit before it. It's going to move between the 4s right there. It's going to go from where it is to there. Notice I'm ignoring this 0 in front. That has nothing to do with the decimal. So it moves 1, 2, 3 places to the right. Therefore, my exponent is going to be 3, but because the decimal, small number, repeated division, -3rd power. Okay? So why do we have scientific notation? What's even the point? The point of scientific notation is to be able to compare numbers quickly. So the table here shows the amount of money that visitors spent in these countries, or from these countries in the United States. So I have some very strange looking numbers, but I can look at the magnitude. They call it the magnitude of these numbers. And the magnitude is based on the exponent. So this has a power of 7. This is going to multiply by 10 7 times. This also has a power of 7. This will multiply by 10 7 times. These only have a power of 6. So multiplying by 10 6 times is going to obviously make your number smaller. So to compare numbers in scientific notation, the first thing you look at is the exponent. A 7th power here is bigger than a 6th power here, no matter what these decimal numbers are. But now since these two are tied, the 7th and the 7th, now I'll break that tie using the decimal number. Which decimal number is larger? Canada's 1.03 or the United Kingdom's 1.06. Obviously 1.06 is larger. So if I want to go from greatest to least, biggest to smallest, United Kingdom is first, and then Canada. So I looked at the exponent first, and then broke the tie using the decimals. Now I have a tie with these exponents also, these 6 powers. So I'm going to break that tie using the decimals. Which has a larger decimal number? Mexico or India? Obviously Mexico. So Mexico comes third, and then India is the least. Comparing the numbers in scientific notation, look at the exponent first. Larger exponent is always larger, no matter what the decimal is. 10 to the 7th power is going to multiply by more 10s than 10 to the 6th power. So even though this Mexico decimal is large, this overall number is going to be larger. Okay? Let's do one more like that, and then we'll be done. Quick clicks. You can read that if you want. Table lists the maximum frequency of the colors in the visible light spectrum. They want to order it from greatest to least, biggest to smallest. So exponents first. All the exponents this time are even. Even exponents with each other means that they're all going to have the same number of places in them. Now I'll just break that tie using the decimals. So since they all have the same exponent, there's not one that's larger than the other based on the exponent. Now I'll break the tie with the decimals. So now the largest decimal is violet, and then it looks like blue, and then green, and then orange, and then red. Let's see how I did. Violet, blue, green, orange, red. But if any of these powers were bigger or smaller, we would immediately have a larger or smaller number without even looking at the decimal number. All right, and that is our quick scientific notation lesson. Have a good day.